Just finished the sticky tape lab, and now we're starting to think about what happened. Why did the aluminum foil move more than the paper? Both the aluminum foil and the paper were neutral, so why did they even move at all? So our essential question, why did the aluminum foil move more than the paper? Well, let's figure that out. First, we have to talk about what neutral means. So neutral means that there's an equal number of positives to negatives. So for this example right here, there's 3 positives and 3 negatives, so we have a neutral. I have more positives, so it is positively charged. I have more negatives, so it is negatively charged. So it has to do with the amount of things contributing to the charges. So before we even moved, our paper and our foil were both neutral. So we had 4 negatives and 4 positives. We had 4 negatives and 4 positives. They looked really similar. They're equally distributed. They just look the same. They're nice and balanced. So when I moved the foil near another piece of foil, it didn't do anything. When I moved a piece of foil near the paper, it also didn't do anything because they're neutral. So they didn't have that overall effect on each other. But when I introduced a charge like that positively charged piece of tape, we saw something happen. We saw that the charges inside the paper and the foil rearranged slightly. And there was a weaker attraction for the paper and a stronger attraction with the foil. So we really want to start to dig in and see what happened here. Why did the paper move only a little bit? And why did the foil move a lot? Well, to understand this, we have to start talking about what a conductor is. So a non-conductor is when charges rearrange, but they don't really move very easily. That's my paper. And then a conductor, well, that's where the charges move very easily. So I'm able to pass those things along a lot better, those negatively charged things. Which brings us to this idea of Thomson. So Thomson was a scientist who played around with these things called cathode rays, where they shot this light particle from cathode to anode. We don't really need to know what those terms mean, but we need to know that there was a particle that went from one side to the other. And eventually, Thomson brings this positively charged thing toward the light, and it bends. And he found that it moved very easily. And after doing some math and geometry, he figures out that this thing is really light. In fact, he finds out that it's 1/2000th of a hydrogen atom, which at that time was the smallest known particle. So he found something even smaller, something negatively charged, that was inside the atoms that he called the electron. So we come up with this new model. So before this, we had the indivisible sphere, our Dippin' Dot. It was given to us by Democritus and Dalton. It's just a ball. Now we have this ball that has positives and negatives to it. So I call it the chocolate chip. So it is a chocolate chip cookie where our positively charged cookie dough, so this is positively charged, and floating around inside there are these negative chocolate chips. Now those negative pieces can be moved. They can be moved within that atom, and they can also be moved away from that atom and taken out and put into something else. So they can move. Now, when they're balanced, we get our neutral atom, and they want to be neutral, which is what's really neat about these. So when we think about the sticky tape lab, what we were doing was we were moving electrons. So at first we had these 2 neutral pieces of tape, right? So each one of these are a positively charged body of a +3, right? So +3 with our 3 negative chocolate chips. We have something that's neutral. We move them together. And when we move them together, those electrons start moving a little bit. And some of them move over to the other side. And when we pulled them apart, those electrons didn't come along for the ride anymore. So we ended up with a positively charged piece of tape. We now have those same positive bodies, the same positive cookie dough, but we have less of those electrons. And we have more of those electrons down here. So we have this positive tape, which was our top tape, and our negative tape, which was our bottom one. And that's what conductivity is. Conductivity is the ability to pass electricity or heat through a material. Metals are really good at this. They're great conductors. So electrons can hop from atom to atom really well. And our question is paper a good conductor then? And how can we explain this difference? Let's take a look at it. So we talked about metals. Metals are conductors. They hop easily. They move very easily between each other. So when I add that positive force, whoosh, they all squish to this side. They're all trying to get as close as they can to that positives. And look, some of the atoms there don't even have electrons anymore as like one. They all squish toward the front. They're very mobile. But the paper acted differently. That's what we call an insulator. That's where the electrons cannot hop between those different atoms very easily. So they do move. They move to the front of those atoms, but they don't leave that atom. So they're not very mobile. Now we want to think about this. If we want to know which ones are metals and which ones are nonmetals, we go back to our periodic table. So which ones are our insulators and our conductors? Well, we have our original 7 here, our little bracket and our hydrogen. Those are our diatomics. Well, everything else that I marked in yellow over here, these are non-metals. These are our insulators. Meanwhile, everything else in red, those are my metals. These are the things where electrons can move very easily. And we're going to learn more and more about metals this unit. But really what we want to know is that metals, the red, pass electrons very easily, while our nonmetals, the yellow, don't. Now the green things in between, we call those metalloids, but we're not going to pay particular attention to them yet. We may get to them just a tad later on, but really what we need to know is that we have nonmetals, yellow, metals, red. And I want you to also alter your periodic table to reflect this as well. That way we can keep track and use this. All right, let's make sure that we're coloring and making good distinctions about this. Don't color it too dark. You still want to be able to read the numbers. Those are going to be important later too. All right, we'll talk to you soon.